Hello viewers, in today's session we are going to discuss another important application of Lagrange's mean value theorem. And in this session we are going to discuss a very important inequality in real analysis, right? And here we have to show that e raised to x minus 1 divided by x is greater than 1 but less than e raised to x for all x greater than 0, where x belongs to the set of real numbers. So we'll show or we'll prove this inequality using the concept of Lagrange's mean value theorem. So before proving this inequality, let us quickly revise the statement of Lagrange's mean value theorem. Now, the Lagrange's mean value theorem says that if we have a function, say y is equal to f of x, which is defined in some domain, and the domain is given by this interval, that is a comma b, and if this function f of x is continuous in the interval, that is the closed interval a comma b, and this function is also derivable or differentiable in the in open interval a comma b, then Lagrange's theorem says that there exists a point c which lies between a and b, such that the derivative of this function at this point, that is f prime of c, is equal to this quotient, that is f of b minus f of a divided by b minus a. So this is the statement of Lagrange's mean value theorem. So we have a function y is equal to f of x, which is defined in some domain a comma b. This function f of x is continuous in the closed interval a comma b, and this function has a finite derivative, or this function is derivable in the open interval a comma b. Then there must exist a point c between a and b, such that the derivative, that is f prime of c, the derivative of f of x at this point c, is equal to f of b minus f of a divided by b minus a. So now the first step in proving this inequality is to construct or frame an appropriate function. So let us take here the function y is equal to f of x, which is x minus e raised to x, and here we'll take the interval that is 0 comma x, where x is greater than 0. So now our function f of x is x minus e raised to x, and the interval a comma b is 0 comma x, where a is 0 and b is x. Right, now see, this x is a polynomial function, right? This is a polynomial function, and e raised to x is our exponential function. So now let us first see these two conditions of Lagrange's mean value theorem. Now see, this is the difference of two continuous functions, because polynomial function is a continuous function for all values of x belonging to the set of real numbers, and exponential function is also a continuous function for all values of x belonging to the set of real numbers, right? So this is the difference of two continuous function, and the difference and the sum of two continuous functions is again a continuous function, right? So here this function f of x is continuous in the interval, that is a comma b. So here we have the interval 0 comma x, because x is polynomial function, this is continuous, e raised to x is exponential function, and this is also continuous, and this is the difference of two continuous functions. So f of x is also a continuous function. Now similarly we can prove the differentiability of this function f of x. Now the polynomial function x is differentiable for all values of x belonging to R, and e raised to x is also a differentiable function for all values of x belonging to R, right? So this function f of x is also differentiable or derivable in the interval 0 comma x, right? So our function f of x is equal to x minus e raised to x is continuous and differentiable. So f of x satisfies these two conditions of Lagrange's theorem. Hence, there must exist a point C between 0 and x, that is 0 and x, such that f prime of C is equal to this expression, right? So we can now write f prime of C is equal to f of x, because a is 0 and b is x, and here we have f of 0 divided by x minus 0, right? So now let us find out the derivative of f of x. So f prime of x is given by d by dx of x minus e raised to x. So the derivative of x is 1 and the derivative of e raised to x is e raised to x. So here f prime of c can be obtained by replacing x by c. So here we have 1 minus e raised to c, and f of x is x minus e raised to x, and f of 0 can be obtained by replacing x by 0. So here we have 0 minus e raised to 0, and in the denominator we have simply x. So now we can write 1 minus e raised to c, and we have x minus e raised to x minus here we have 0 minus 1, because e raised to 0 is 1. So here we have x, so we can now write x minus e raised to x plus 1. So this minus and this minus, it becomes positive, and here we have x. Now we can transfer the quantities here. So we can rewrite this equation as e raised to c is equal to 1 minus x minus e raised to x plus 1 over x. So we can now write x minus here we have positive e raised to x minus 1 over x. So simplifying this expression by multiplying this 1 by x, and here we have minus x, then plus e raised to x and minus 1. So this x and this x get cancelled, and we are left with e raised to x minus 1 over x. So now we have this equation, that is e raised to c is equal to e raised to x minus 1 over x. So now we have this expression, right? Okay, now let us make use of this inequality. Now this c, it lies between 0 and x. Now what we will do, we'll raise these three terms to the power of e, right? So we can write e raised to 0, and here we have e raised to c, and here we have e raised to x. Now the direction of the inequality remains the same when we raise these three terms to the power of e, because the exponential function is an increasing function, right, for all values of x. So now here e raised to 0 is 1, and here we have e raised to c, and here we have e raised to x. So the purpose of raising these three terms to the power of e is to get e raised to c, and here e raised to c is e raised to x minus 1 over x. So here taking e raised to c as this expression, we can now write 1, and here we have e raised to x minus 1 over x, and here we have e raised to x. So this is our required inequality, that is e raised to x minus 1 over x, it lies between 1 and e raised to x for all x greater than 0, where x belongs to the set of real numbers. So viewers, this is how by the application of Lagrange's mean value theorem, we can prove this important inequality. So now let us take two important result or deductions using this inequality, right? Now see, if we take limit x tends to 0 throughout this inequality, right? So now we are making two important deductions using this inequality. So the first one will use the concept of sandwich theorem or the squeeze theorem. Now what we will do, we'll take the limit x tends to 0 throughout this inequality. So here we have limit x tends to 0 1, and then we have limit x tends to 0, and here we have e raised to x minus 1 over x, and here we have limit x tends to 0 e raised to x. Right now see, this expression or this limit is simply equal to 1, and here we have limit x tends to 0 e raised to x minus 1 over x, and this limit, that is limit x tends to 0 e raised to x is simply e raised to 0, that is 1. So here we have 1. So now by using the concept of squeeze theorem or the sandwich theorem, the value of this limit is equal to 1, right? So we can now write limit x tends to 0 e raised to x minus 1 over x is equal to 1, and this is an important result in limits. So now see, here we have used the concept of sandwich theorem, right? Now if we take this function as say g of x, and this function as f of x, and this function as h of x, right? So sandwich theorem says that if we have three functions, g of x, f of x, and h of x, such that these three functions satisfy this inequality, and if the limit x tends to a, g of x is L, and limit x tends to a, h of x is also equal to L, then the limit of this function is also equal to this number L, right? So sandwich theorem says that if we have three functions, g of x, h of x, f of x, and h of x, and satisfying this inequality, and if the limit x tends to a, g of x is L, and limit x tends to a, h of x is also equal to L, then the limit of this function when x tends to a is also equal to L, right? And here g of x is 1, f of x is e raised to x minus 1 over x, h of x is e raised to x, right? So here we have seen that the limit x tends to a g of x, that is limit x tends to a, for a we have here 0, and for g of x we have 1, this is 1, and limit x tends to 0, and h of x is e raised to x, then this limit is also equal to 1. So the value of L in both the cases is 1. So the value of this limit, that is limit x tends to 0, f of x is equal to 1. So now let us make the second deduction or the second result. Now see, here if we integrate throughout with respect to x from 0 to 1, then we can write 0 to 1, and here we have 1 dx, and then here we have 0 to 1 and e raised to x minus 1 over x dx, and here we have 0 to 1 and e raised to x dx, right? So what we have done here, we are integrating throughout from 0 to 1, right? Now the value of this integral is given by x 0 to 1, and here we can take this integral as I, and here the integral e raised to x is simply e raised to x, and limits are from 0 to 1. So here we have 1 minus 0, and here we have I, and here we have e raised to 1 minus e raised to 0. So this is 1, this is I, and this is e minus 1, right? So the integral of this function e raised to x minus 1 over x from 0 to 1, which we are taking as I, it lies between 1 and e minus 1, right? So this is another important deduction using this inequality. So here we have used another important result from definite integrals, right? Now see, here we have seen that one is, we have assumed g of x as 1, this function as f of x, and this function as h of x, right? So the properties of definite integral says that if we have three functions, g of x, f of x, and h of x, such that these three functions satisfy this inequality in some domain, say a comma b, then the integral a to b g of x dx is less than or equal to the integral a to b f of x dx, and this is further less than or equal to a to b f of x, sorry, here we have h of x, so here we have h of x dx. So if we have three continuous and differentiable functions such that g of x is less than or equal to f of x is less than or equal to h of x in some interval a comma b, then the area bounded by this function is less than or equal to the area bounded by this function f of x, and which is further less than the area bounded by h of x. So here we have integrated throughout from 0 to 1. A is 0 and b is 1, right? And we have obtained this inequality, or this integral inequality, that is I is greater than 1 but less than e minus 1, right? So viewers, this is how we can make two important deductions using this important inequality.